We were looking at the Kepler problem last time, and we looked at the curve of effective potential, and it looked like what you have on the right hand side here. Okay, and we saw that it has a minimum, which is, it has only one minimum, and there are no other extremums, and the curve has this shape, and we want to analyze this Kepler problem further. Okay, but before we do so, let's just have some fun today with learning about some curves in polar form. So usually we are more familiar with curves in Cartesian coordinates, and today I would like to discuss about them in polar coordinates. So one of the simplest curves, one of the simplest ones, is a circle, and its equation is x square plus y square is equal to 1 if it is a unit circle. Okay, and it is centered at the origin. What does it look like in polar coordinates? The same equation, the same circle. In polar, it looks like r is equal to 1. Now I will shift this circle along the y-axis, meaning I will take its center to lie at y equal to 1. So I shift it so that you have this. So the center is shifted to 1. Okay. Now what is the equation of this circle? So let's look at what it looks like in Cartesian. It looks like x square plus y minus 1 square equal to 1. Okay, let me draw the circle again so that those of you who are seeing it on smaller devices can see it easily. Okay, and this is your center of the circle, and this is the origin. So the circle is touching the origin, and we are measuring with respect to here. So let's say this is some point P on the circle, which has a radius r and makes an angle theta. Forget this. Okay, it makes an angle theta, and I want to know the equation of this circle in r and theta. So you put x is equal to r cos theta and you square it. Then you put y to be r sin theta, and then you have a minus 1. You square it, and that should be equal to 1. Now let's just do this very trivial algebra. I'm doing it because it's so trivial to show. So you open it up, it gives you an r square sin square theta that I will combine with this term, first term. Then you get a 1, and then the product, okay, the cross product. So I get this plus the first term from here gives me r square. Okay, I have used sin square theta plus cos square theta equal to 1. Then I have minus 2r sin theta, minus 2r sin theta, and then you get a 1 from here, but that cancels with that 1 here, so I get a 0 on the right hand side, which I can factor into r minus 2 sine of theta, that is equal to 0, and which immediately gives you the equation to be r is equal to 2 sine theta. Okay, so the equation of this is r is equal to 2 sine theta. Okay, you can change the radius to something else. Let's say that if the radius was not 1 but was a, okay, then this will become r is equal to 2a sine theta. Okay, so that's what it looks like in polar coordinates. See, if you are given sine theta and you plot it in the Cartesian coordinates, you get the sinusoidal curve. But if you plot sine theta in polar coordinates, you get a circle. Okay, now we will ask, let's ask what would the equation of the circle would be if you shifted the circle along the x-axis. Along the x-axis. If instead of this you had, let's say, this thing. So if you have a unit circle which is just touching the coordinate axis, what will be the equation for this? And you should find out that this has a polar equation, r equal to 2a cos theta. Let's see whether it looks reasonable. So when theta is 0, I should get r to be here, which means 2a. Cos 0 is 1, so 2a. So looks good. Okay, please check that this is what you get for this circle. Now, next we would like to ask, what are the polar equations of parabola? So I would like to ask now, if I am given a parabola, okay, what does it look like in polar coordinates? This or this. Okay, so let's look at this now. Okay, before I move on to polar equations of parabola, I want to encourage you guys to use some programming language to do, for example, plotting and solving things. Okay, so this skill you should have, and I have here Mathematica in front of me. I believe you can access Mathematica for free online. Okay, so there is some freely available thing available from Wolfram. I checked the website, so I thought that maybe I'll show you how small things you can do here. This one is not free. This one is through my institute subscription, but you can search online. So let's say I want to just let me show you addition of two numbers here. So I write 2 plus 2 and I hit shift enter. Okay, so I should be pressing shift and then hitting enter. It calculates and you get 4. Okay, so that's the way. So it shows, I hope you can see here easily. Let me see if I can. Anyhow, so here it is line in 1, meaning I have input 1 here, 2 plus 2, and output 1 is 4. Okay, if you want to plot something, let's say you have some function sine of x. Okay, so here is the syntax. The sine should be written with capital S, and the function argument has to be in the square bracket. Okay, so that's what I'm doing. X ranges from, let's say, 0 to 2 pi. Pi, okay, so capital P, and for the plot, so I'm plotting this. You can learn the syntax on your own. I don't want to spend time on that. I just want to encourage you to do this. That's why I'm doing it here. So you get the sine function. Okay, that's the plot of sine function, which you know. Now let's do our polar plot. So I said that if you want to look at a circle, it will look like 2a sine theta, or 2 sine theta for a unit circle. So I want to plot it, and it is called polar plot if you want to plot in polar coordinates. So POLAR, capital PLOT. So I open and close the square brackets, and what do I want to plot? I want to plot sine of theta. Let me call theta as t, and the values of t should run from 0 to 2 pi. Okay, and let's see what I get when I do this. And you know what I should expect? I should expect a circle, right? Remember, sine theta is a circle in polar coordinates, and that's what you get. And you see here it is touching the x-axis on the circle is touching the x-axis. Okay, you may also see, let's say I change sine of t, okay, to cos of t. I can plot both the things together, but I don't want to do it right now. So cos of t here. Let's see, what do you expect? You expect the circle to be having its center on the x-axis. Okay, so this is what you get, let's say. Nothing happened, and there has to be something. Yeah, mistake. So because I have written cos t here, it should have been cos. Let me again shift enter. Let's see. Perfect. Okay, so please learn one programming language which you can use to do all these analytic manipulations, and Mathematica is one of them. You can use anything, any programming language. I'm not going to base any of the questions on Mathematica. So if you don't learn this, no problem at all. But if you learn it, it will be very good for you. Okay, and given that it is free, as far as my understanding goes, it will be very good for you. Okay, good. So we'll continue with parabola, and also I will show you some plots in Mathematica for parabola after we have derived the equations. Let's recall what a parabola is. It's a set of points which are at equal distance from a given point, which we call focus, and a given line, which is called directrix. Okay, so let's say this is my y-axis, that's my x-axis, and I choose that given point to be, or the focus to be here, a distance a away from the origin. Okay, and I want my parabola to have its vertex here at the origin. Okay, so which means that if this point has to be equidistant from this point and the given line, then the directrix should also be a distance a away from the origin. So my directrix will be passing through this. Okay, so this is my directrix. Okay, now yeah, so let's say I draw a line parallel to the directrix or x-axis from here. This length is 2a from here to here, so I mark a length 2a here on this side, and similarly 2a on that side. So clearly, because this length is equal to this length, my parabola will pass through these 2 points as well, and then I can draw my parabola to be like this. Okay, and here. So that's our parabola, and you know what the equation it has in Cartesian coordinates. It is x equal to 1 by 4a y square. Okay, this is y. Sorry, yes, correct. This is x. Okay, that is fine. All good. Yeah. Now let's find out what the equation looks like in polar coordinates. But before I do that, I want to shift the origin from here to the focus. So first I do shift the origin to the focal point, to the focus. Okay, so which means I start with this equation which I have here. X is equal to 1 over 4a y square, and shift my x-axis such that focus is the origin is here. So I should write x plus a whole square 1 upon 4a y square. So after shifting the origin to the focus, mistake here. I get x plus a as 1 over 4a y square. Okay, so here in this equation I have just shifted the origin. So now let's substitute x equal to r cos theta and y equal to r sin theta in this equation, and I get r cos theta plus a is equal to 1 over 4a r square sin square theta, which I can write as 1 over 4a r square 1 minus cos square theta. Okay, good. So I take this term cos square theta on the left hand side and get r cos of theta plus 1 over 4a r square cos square theta plus a equal to 1 over 4a r square. Okay, and you will be able to solve it. It's a quadratic equation, and you can solve it for, just complete the square, and then you can write the following. So from this you will be able to show that r is equal to plus or minus of r cos of theta plus 2a. Okay, it's a trivial algebra that you have to do, and of course you get two possible solutions from here, which are the following. Maybe I should go to next page. So you get one solution as r is equal to minus 2a, remember a is positive, 1 plus cos of theta. That's one possibility. Another possibility is r is equal to 2a over 1 minus cos of theta. Okay, and you should try to plot these two curves and you will get the following. You already know what you will get because that's what you have constructed. So this one will correspond to this, which is what we started with. This is the origin. Okay, and this one also corresponds to the same thing. No surprise, because that is what you started with. Okay, so there are two, these two equations give the same parabola, okay, at the origin. I will encourage you to also check the following, that if instead of the above you choose r equal to 2a over 1 plus cos theta, then you get the following. You get a parabola like this, but this time it is opening up on the left hand side. Okay, and similarly here, if you put r equal to minus 2a over 1 minus cos of theta, then you get this parabola. Okay, so Yeah, that's the equation of a parabola. So you have some number in the numerator which controls the, you see what this 2a is, look at the 2a here or here. Okay, this 2a is just the distance of the vertex from the directrix. Okay, that's what it is. And then you have 1 plus cos theta or 1 minus cos theta in the denominator. Okay, that's good. Next I would look at an ellipse. Okay, and write down its equation in polar coordinates.